A used car company estimates that certain new cars lose 1/8 of their value each year. So for part A, we want to write an equation to model the value of the car after T years if the car costs $35,000 new. And we're going to look at this situation numerically. And remember, numerically just means that you are going to make a table. So we'll start by comparing the two quantities that are changing. So we have the value of the car that's changing, and then time, how long we've owned the car. So because the value of the car depends on time, time is going to be our independent variable. So we're going to have the time that we've owned the car, and I'll use V for value, but you could use any variable that you want. So let's go ahead and write our variable key. They gave us that they wanted the input to be T, time, in years. So T will be the number of years that we've owned the car. And then we're defining V as the value of the car. And that's going to be a value measured in dollars. All right, so we know that the car was $35,000 new. So that would be at a time 0, the car's value is $35,000. So now we want to figure out what the car's value is after 1 year. 1 year after we've owned it. Now what's the value of the car? And it's losing 1/8 of its value each year. So grab your calculator and let's number crunch a little bit. If we're losing 1/8 of our value, you might start by taking the $35,000 and multiplying by 1/8. But if you go ahead and do that, 35,000 times 1/8, we'll have 4,375. This is not the car's value. This is going to be the change in value. In fact, this is the amount that the value has decreased. So to get the actual car value, we would really need to take this value and subtract it from the original value of the car, from the 35,000. So really we would need to take 35,000 minus 4,375. And remember, it's really important that you're doing these computations on your own on your calculator. So don't forget to stop the video at any time, pause it, and make sure you do your computations. So the value after 1 year is going to be $30,625. And then we could do a similar computation to get the value of the car after 2 years, and after 3 years, and so on. But we want to figure out what the pattern is here, if it's losing 1/8 of its value. So let's take a look at all these computations here that we just did and see if we could actually streamline the process a little bit. This is kind of the long way of approaching the problem. Could we make it a little shorter? And in fact, if you look at this very first step, the 35,000 minus the 35,000 times 1/8, we could actually think of that first step and change it into a factoring problem. We could factor out the 35,000. And you should be left with 1 minus 1/8 if you factor out the 35,000. In other words, this is the same as taking 35,000 times 7/8. And go ahead and check this. Put this in your calculator. 35,000 times 7/8 is going to give you the $30,625, the worth of the car after 1 year. So that's a little streamlined. That's going to be a little more efficient method. And it's also going to help us figure out what our multiplier is then over here. To go from 35,000 to 30,625, we need to multiply by 7/8. Multiply by 7/8. Sorry, having trouble writing that multiplication symbol. There we go. Okay, multiply by 7/8. That's going to be our multiplier. So another way to think about this is to go up top here where we decided that the car is losing 1/8 of its value. You might make note that that would be equivalent to maintaining 7/8 of its value. So if it loses 1/8 of the value, then it's going to maintain 7/8 of the value. And that's another indicator that we have a multiplier of 7/8. So now if we do the same thing and we now take our previous entry of 30,625 and we're going to go ahead and multiply by 7/8, now you can get the value of the car after 2 years, which would be, it looks like 26,796.875, or in other words, 88 cents. And then you could do it again to figure out the value after 3 years. But usually at this point, we see that our pattern is we're multiplying by 7/8 each time. That's going to tell us that this is exponential decay, and we should be able to write our model. All right, so remember, whatever your multiplier is here is what we're going to use for the base in our equation. So we would go ahead and start with a basic equation of the value of the car. The base is 7/8, and then we'd be raising it to the power of x, or in this case, t. But we need to make sure that our values are going to work in this model. So, for example, when we input 0 for time, we need to get out 35,000. And if you input 0 for time in this model, in this equation, 7/8 to the 0 power, you're going to end up with 1, not 35,000. So therefore, we actually need to have a coefficient out in front here. So think about 7/8 to the 0 power is really going to give us 1, and we want it to give us 35,000. So we need to have a coefficient of 35,000. So we can fix this. Hopefully you're taking notes in pencil. So we adjust our model here to make it match our table. 35,000 times 7/8 to the t power. And then I always recommend that you take one of these other values in your table, these ordered pairs, and just test it out. For example, substitute in 2, 35,000 times 7/8 to the second power, and make sure that you're getting the 26,796. But I believe you are. So part A, we have our model. So part B. Part B says, what is the value of the car after 5 years? What will the car be worth? So that's just a matter of us finding V of 5. And you can certainly use your calculator for that. Just make sure that you do have the 7/8 in parentheses. And then you're going to go ahead and input 5. So again, take your time doing that on your calculator, but it appears that the value after 5 years is approximately $17,951.81. That was a decimal point. $17,951.81. All right, so lastly, let's go on to part C, which is when will the car be worth $10,000? So now we're searching for when the car is going to reach this value. So in other words, now we're interested in solving for time. We're solving for t. And I'm giving you the value of the car, the $10,000 is the V. So substituting, that's going to give us this equation. 10,000 is equal to 35,000 times 7/8 to the t power. And so we need to solve this equation. And remember, this is an exponential equation because we have the variable up in the exponent. So to solve your exponential equations, you want to start by isolating the exponential quantity. So the exponential quantity here is the 7/8 raised to the t power. So we'd want to begin by dividing both sides by 35,000. So we can isolate what I have circled in red. Divide by 35,000. So that will give us 10 divided by 35, which if you type that in your calculator, that is going to be a decimal, but it's not an exact decimal. And so you don't want to round in the middle of the problem. We only want to round at the very end, one time. So you want to go ahead and keep this in exact form. So 10 over 35 would be fine, or you could go ahead and simplify your fraction. And that's equivalent to 2/7, 2 over 7. So now we have 2 over 7 is equal to 7/8 to the t power. So now, still an exponential equation, we want to try to get the bases to be the same. Because remember, if we can get the bases to be the same, we say if the base on the left is b. And the base on the right is also b. If the bases are the same, then that uniqueness property says that the exponents will be equal. So that's the uniqueness property. So going back to our example here, the question is there any way that we can get the bases to be the same? When the left side, the base is 2/7, and the right side, the base is 7/8. And the answer to that question is going to be no. There's no way we're going to be able to get those bases to be the same. So we need to solve this equation a different way. And we're going to solve it graphically, and we'll go ahead and use our graphing calculators for right now. So we're going to graph the left side in our y1 and graph the right side in your y2. So in your y1, go ahead and type in y equals 2/7. And then in your y2, go ahead and type in y equals 7/8 raised to the x power. So remember, you're not going to have to type in the t. You'll just type in 7/8 raised to the x power in your graphing calculator. And then what we want to do is calculate the intersection. So we're going to solve this graphically by using our graphing calculator to graph the left side of the equation and the right side, and then we're going to calculate the intersection. So pause the video for a second and see if you can get a decent window that's going to allow you to see both of these curves as well as see the intersection. Keeping in mind that the left side, y equals 2/7, should just be a horizontal line, and then the right side, the y equals 7/8 raised to the x power, that should be a nice exponential decay function. It should be a decreasing function because the base is smaller than 1. So I went ahead and graphed it. I hope you paused your video. And the window that I used, if you're struggling with your window, I did an x minimum of -2 and an x maximum of 20. And then because 2/7 is such a small number, I chose my y minimum to just be -1 and my y maximum to be +1. There was no need to make my y values very large. And in this window, I was able to see the intersection clearly and then calculate the intersection. And in my intersection, I had an x value of approximately 9.38. So that would be my t value. It's t on our paper, but that's in the calculator the same as x. So t is approximately 9.38. And then looking at your variable key, remember, t was time measured in years. So it's going to take approximately 9.38 years for the car to be worth $10,000. So that's how you would solve this exponential equation graphically, since we couldn't get the bases to be the same and use the uniqueness property. Now what's to come in the future is learning actually how to solve this algebraically, and that's the motivation for needing logarithms. Turns out we're going to need a logarithm to solve this exponential equation algebraically. But stay tuned, that comes in a couple days.